Ciao, and welcome to the Frontier Space Podcast, a dialogue about how space technology and exploration are transforming our solar system.
Hello, Vasco. We're delighted to have you here today on the Frontier Space Podcast.
Thank you. It's also a pleasure to be here.
Well, wish we made it to the SSP with ISU last summer.
Yeah, it was our first meeting. It was a good opportunity for me also, because I came from a community that is not directly the space community, came from plasma physics. And of course, we will discuss a bit this during this podcast, I guess. But yeah, we are trying to join our plasma with the space activity. So it was a great opportunity for us to meet at ISCC.
Nice. Seems like a lot of it really interesting and forward-moving research on plasma reactors and carbon dioxide decomposition and everything you're into.
We are, as we are saying, we are bringing our plasma into this possibility to, take advantage of natural resources on Mars in this case. So it was a decomposition of carbon dioxide that exists on the Martian atmosphere in abundance. So essentially, Martian atmosphere is carbon dioxide. So about 96% of the atmosphere is composed of carbon dioxide. And we are trying to decompose it to extract the oxygen. So then we can also see a bit what we can do with the oxygen, but plenty of things, in fact. But that's the broad idea is that one. So I don't know exactly in each order if I just move on and start discussing a bit, or if you want to guide me a bit on the discussion.
Yeah, I think a general kind of background in terms of what exactly is plasma and how this influences gases and
so let's start from the beginning. So plasma, anyone that Googles and finds in Wikipedia will read that plasma is the fourth state of matter. So this goes on a little bit the image we get from elementary school of states of matter. So if we start with ice, with a cube of ice, and we start heating, so we are putting energy into the system, then after a while we will melt and we will have this phase transition from solid to liquid. We are all familiar with this, and then if we continue to supply energy to the system, then the bonds between the different molecules will break and the molecules separate, and we have gas. So we have another phase transition to vapor or to gas. And then one obvious question is, what happens if we keep heating the system, if we keep supplying energy to the system? And the answer is that after a while we have enough energy so that some of the electrons start to really be separated from the nucleus. So in other words, the gas starts to ionize. And that's the transition to the plasma state. So plasma is, first of all, ionized gas. This is a nice image, and I always like to remember the Greek and classical antiquity, where they had this image of elements, earth, water, air, and fire. And these are, in fact, the four states of matter, not the elements, but the states of matter. So solid, liquid, gas, and plasma, because fire is, in fact, one example of a natural plasma. So it's an ionized gas, first of all. And then there are more elements in this definition. I will just mention them for completeness. So it's an ionized gas that is quasi-neutral, which means about the same number of positive and negative charges. And then we add to the definition, it exhibits a collective behavior. So I will not dwell now what exactly this means. But this collective behavior is induced because the kinetic energy, average kinetic energy of particles should be much larger than the interaction potential energy. So yeah, this is a bit strange maybe, but on a second thought, it's a natural constraint, because if the potential energy is very big, the electrons will recombine with the ions immediately and we lose the plasma state. So we need to have a lot of thermal agitation, so a lot of kinetic energy of the charged particles. So this is a textbook definition of plasma. And then, of course, we start thinking, so why plasma can be interesting for this application? So going back to the broad or main idea regarding this in situ resource utilization on Mars, so we have carbon dioxide there. We want to break the molecule. Carbon dioxide, we know from Earth and global warming and so on, that it's a very stable molecule. So it's very difficult to break. So we need a lot of energy to do that. But if we have this plasma, so we have free electrons. Electrons are very light, so their inertia is very small. And they are charged, so we can accelerate them easily with electric fields. So that's another important aspect. So with electric fields, we accelerate electrons very easily to relatively high energies. And then when they are going very fast, it's almost a cartoon image. Electron comes very fast, collides with carbon dioxide molecule and breaks it. And so we have part of the mechanism. It's these electrons that transfer their energy in collisions to the carbon dioxide molecule and actually break it. And then we start having a mixture, carbon dioxide, maybe carbon monoxide, but also the oxygen we are interested in. And that's already an important aspect of the problem. So one question that appears or that is important to consider is that Martian natural conditions are very good for this process to occur. Because we can ask the same question, so can we do this on Earth? Or what is different between Earth and Mars? We can do it on Earth, but Earth has a much thicker atmosphere. And so it's, I don't know, roughly 150 times thicker than Martian atmosphere. And if there are many molecules around, when the electrons start to accelerate from the electric fields, they start colliding before gaining enough energy to dissociate. So the electrons start gaining energy, but immediately they collide. So it's a process with a lot of friction, so to say. And in Mars, because the pressure is a bit lower, the electrons have time to fly a bit before they collide, so they gain energy that it's enough to dissociate the molecule. So this is another aspect that is interesting for plasma, is that the natural conditions on Mars are quite good for the plasma operation, in particular pressure conditions. Also, temperature is interesting, but less critical than pressure. Also, the minor constituents of the atmosphere of Mars, nitrogen and argon, are interesting for plasma operation, but maybe I will skip these details at this moment. And this is the zero order effect. So we have free electrons that are accelerated by electric fields, and they collide and dissociate the molecule.
Yeah, that's awesome. Thanks for this kind of this picture and video in our minds. This complex plasma chemistry on top of the it's like the electrode layer of the solid oxide membrane.
Yeah, so this is the next, and at the moment the technical, the more challenging aspect of it is that once you have this soup with carbon monoxide, carbon dioxide, oxygen atoms, oxygen molecules, and so on, we need to extract the oxygen. And so that's a very big challenge, and presently the bigger challenge. Dissociating the carbon dioxide, okay, it's difficult to make it very efficiently, but more or less we know how to do it in a reasonably efficient way. But the real difficulty at the moment is this separation of the oxygen. So this is work that is being led mainly by our colleagues at the Netherlands, at the Dutch Institute for Fundamental Energy Research, that are working with these solid oxide membranes. Of course, we need a very pure oxygen stream after all this process, because we want to have oxygen, okay, maybe for breathing in a small environment. It's not terraforming Mars, but it's to have some available oxygen for life support in small rooms or whatever. And also this oxygen can be used for production of propellants, of fuels to return back to Earth. So again, on the cartoon image, I used to say, okay, let's build a gas station on Mars. So we have oxygen to breathe, but we can also use oxygen and the carbon monoxide that is also separated to produce fuels for rocket propellants. So that's also quite exciting. So this separation is yeah, really work in progress, and it's the main bottleneck at this moment. We have very nice preliminary results, very recent. Nothing is published yet, so it's a work in progress. But there is a proof of concept internally. So we managed to couple for the first time plasma with the solid oxide electrolysis cells, and to see oxygen on the other side. Still many things unknown. In some conditions, this is not working as we would expect at first. We need to fully characterize, but it's looking good. It's looking promising.
Was it like what was the composition of oxygen on the other side? Was it like upwards of like over 90%, close to like
no, it will be 100%. So we cannot afford to have impurities, in particular carbon monoxide, because if we want to use this oxygen for breathing, we cannot have any contamination. So these membranes is a good image for these cells. They permeate only oxygen. So the oxygen atoms will stick to the surface, and then they will, or maybe the molecule, but then they have to dissociate, and then they will be negatively charged. They will capture electrons, and then these negative ions will be transported on the vacancies of the material, and that's it. So on the other side, we extract only oxygen.
Was reading the publication. You mentioned the molecular oxygen radicals there, like travel through the vacancies of the membrane.
Yes. So that's in fact what is traveling is it's atomic oxygen, but on the adsorption. So before it starts being transported across the membrane, maybe it's molecular oxygen that is absorbed. So we have a mixture of many things, So some atomic oxygen will absorb, some molecular oxygen will be absorbed. If it is molecular oxygen, we have to dissociate it on the membrane. And then it has to become negatively charged. And what is transported is actually the double negatively charged oxygen ion on the membrane. And so then on the other side, so when this permeation is complete, so the reverse process somehow has to occur. So we recover, we recombine, and the molecular oxygen will dissolve.
It seems like there might be a certain kind of amount of material degradation or corrosion over time with that membrane. I'm curious.
Yeah, well, all these are challenges, of course. So this is part of this, the lifetime of the system. So we have not yet studied this in detail. So we are in a prior phase, and the more a proof of concept phase, and on the engineering phase. But this, of course, this will be concern. We are rather optimistic that this can operate for many hours. We don't need, in principle, to have external heating to the system, but there will be heating, so there will be transport the energy from the plasma itself, and we'll heat the membrane. So there are many engineering problems to solve later on. So
exciting
one
puzzles.
related,
yes, but
yes,
important
yes.
ones. So
in the end, that's what counts.
In the experiments you mentioned about a Yttria based reactor and the dielectric barrier discharge DBD reactors and these fast ionization waves in a pulse regime of 100 to 1 kilohertz. So it's like some epic experiments.
Yes, so okay, we need to choose the plasma source that we want to use in the end. So what is the best? So we are exploring many different configurations for now, but still in a characterization phase, because in the end the final design and this, well, if we want to really develop a prototype, we will need to have an integrated view. So we know more or less the behavior of different plasma sources. So we can excite with RF radio frequency, or with a microwave, or this dielectric barrier. So we can try different plasma sources. What they will change will be the plasma composition itself. So how fast our electrons, how energetic they are, what is the fraction of molecules that is actually ionized, how big is our dissociation. So they will change a little bit these characteristics, and then we need to couple with this membrane part, with the separation. Then okay, we also need to choose the exactly materials for it, although it is more or less stabilized, but in the detail we need to see the geometry. So how close, how far of the plasma to have the membrane, maybe directly in contact with the plasma, maybe a little bit afterwards. So all these things have to be studied carefully. At this moment, we are, again, the plasma we more or less know for different plasma sources, different excitation conditions, and we are choosing a configuration that is convenient to couple the plasma with the membrane. So to prove this concept that plasma can actually enhance the performance of this membrane. compared to no plasma at all. So because if we look at MOXIE, so the machine, the NASA machine that is actually producing oxygen on Mars already, it uses also one of these solid oxide electrolysis cells. But the concept is very different because they took advantage of technology that exists on Earth, which is evidently a smart thing to do. But if I put it in a very simplistic way, if you take a technology from Earth to Mars, the first thing that you have to do to operate it is to recreate the conditions on Earth. So you arrive on Mars, you face atmosphere that is thinner, so pressure is smaller than on Earth, that is colder. And so the first thing that you have to do is to compress the atmosphere and to heat your gas. And then you use this technology that is available on Earth. So essentially, it's CO2 that absorbs on the membrane, and then it catalytically and enhanced with heat. You dissociate the CO2 on the membrane, and again, then it's the process that I was describing. Then you have oxygen, you charge negatively, and you transport along the vacancies. But so the MOXIE, so the NASA machine, which of course is an amazing achievement and inspiration for all of us, it spends most of the power by recreating the conditions on Earth, so by compressing and by heating. What we are looking at is a alternative or complementary approach where we put more energy on the creation of the plasma and the dissociation of the plasma, of the CO2 molecule, sorry. And then we don't need compression and we don't need to heat because already dissociation is pre-made in the plasma and the plasma will transport the heat anyway. So it's the concept is in one way very different from MOXIE, in another way very similar. But yes, where you put the power and where you spend your energy is in very different places.
Cool. I think we have a better understanding now, and it's also really interesting to learn about how CO2 splitting has 25 vibrational levels with the vibrational translation and vibration relaxation reactions, and
yeah, so like this is
applies to a lot.
Yeah, it's a very I like that part very much. I have to say, because it's from my prior formation. But in reality, I was not telling the complete truth when in the beginning I said that pressure on Mars is perfect because for plasma, because electrons fly and they accelerate and they gain enough energy, and when they hit the CO2 molecule, they will dissociate it. Okay, that's true, but only part of the truth, because they will also be able to put the molecule to vibrate. And in fact, most of the times they will not dissociate the molecule of CO2 when they collide. They will just put the molecule to vibrate. So the first reaction is that, oh, this is disappointing because we want to channel all our energy into the dissociation, so not to the vibrations. That seems like we are losing energy. But in reality, there are two things related to these vibrations. The first one is that if we dissociate directly with a collision by the electrons, we need to go through a highly excited electronic state. So we spend more energy than we need. So the dissociation energy is like 5.5 electron volt, and we need to spend like 7 electron volt. So we need to go above if there is a direct electron impact. And if we manage to do it just vibrationally, we don't need to go so high. When the molecule is vibrating with an amplitude that is large enough, it will break. So we don't need to go above the 5.5. The second thing is that we can maybe take advantage of this internal energy, of this energy in the vibration. So maybe it's not actually lost. So in some conditions, when the molecules, the vibrating molecules collide, they manage to exchange vibration quanta, meaning one molecule, when two molecules collide, one becomes vibrating even more, and the other, of course, loses energy, but we take advantage of the one that vibrates more and approaches this dissociation. So we can use and we can get some help from this vibration energy to overcome the dissociation barrier, which is quite interesting. Another thing is that it's not completely lost because it will heat a bit the plasma, and maybe we will need this heating again to help on the membrane. So that's also a path that we are exploring a bit. So it's already a bit of optimization on the dissociation process. So take advantage of the energy that is channeled to the vibrations. Okay, maybe we can be smart enough to, instead of seeing it as a loss, to take it in our advantage. Also, the absorption on the surfaces can be interesting with vibrating molecules.
Nice. It sounds like you guys also had some significant results with the plasma reactor in the synthetic Mars atmosphere.
Sorry, I didn't really understand.
It sounds like you had significant results with the plasma reactor in the synthetic Mars atmosphere as well.
Yes. So it's a twofold investigation. Because, okay, all this started very conceptually. Yeah? I will not say theoretical because that's a bit too strong expression, but it started, with idea. So, well, finally, I will use theoretical with a theoretical prediction that all these Martian conditions would be good, and we made a very first preliminary simulation to support our arguments, and then we first step was that, okay, we have to go to the lab and to have a minimum evidence that our claims are meaningful. So we went to the lab to ignite the plasma in realistic Martian conditions, so meaning synthetic Mars composition. Very easy to model and to make simulations because with geometry, gas flow were not a problem. So these experiments were made by our colleagues in France, the Laboratoire Physique des Plasmas in École Polytechnique. It's another partner of the project. And they characterize the degree of dissociation and the vibration temperatures that we have on the different modes. And we managed to interpret and explain what was observed. So first we observed CO2 dissociation of the order of 20-25%, which is quite good, considering that is a reactor for fundamental studies, and it's in line with values in the literature. And then the second aspect, I said it's twofold. So first, to experimentally show that this is possible. And the second is that because it's such a controlled reactor, we have the perfect tool to develop a model that describes the plasma chemistry in Martian conditions. So this means that we can validate and tune all our reactions, the different rate coefficients and so on, by comparing our simulations with the experimental data. So this was a successful achievement, I think. We have seen the CO2 dissociation in Martian conditions. Nice. We have verified a little bit of positive effects of this composition. And at the same time, we managed to develop a model for the plasma quite well validated, and we can now use for more complex reactors to help on the design and so on.
Awesome. And so with this compressed gas, passing it through the plasma field and the membrane, and so you guys are proposing this demo with a I think it was like a 25 by 20 by 5 centimeter large kind of shoebox, I would say, to and these estimates are around looked quite exciting and surprising.
Yeah, so this is okay. Of course, we started with let me say head on Mars and a little bit head on the air. Just this is exciting. We can do something interesting. But of course, then we need to sit down and to work out the numbers and see if this can be really something that is potentially interesting, or is just possible, but in a very inefficient way, so inefficient that it's not interesting at all. And from the beginning, we had these numbers that you are mentioning. So of course we have a standard. So again, MOXIE, so NASA machine sets up a standard. It's working, it's there, it's very robust. They are working on how to improve it, of course. So it's only expected to perform better than what is performing at the moment. But this gives already a benchmarking. So the MOXIE is this shoebox about 25 centimeters side. It weighs about 15 kilograms and is producing oxygen at a rate about 5.5 grams per hour. So it's what they are, the numbers that are announced more or less like this. So we were estimating if our plasma reactor could be competitive with these numbers. Of course, for the moment, all these experiments and data that I mentioned, they are made in a very ugly and very heavy reactor. So nothing optimizing, it's a proof of concept. So we are not too much worried with it. But if we want to be realistic, we start thinking, and we can have a reactor that is more or less the same shoebox, but with one dimension less. So something like 25 times 5 instead of times 25. So that makes it shorter, smaller,
Nice.
sorry, smaller.
Nice.
And also instead of 15 kilograms, we believe that we can do with all the shielding components, plasma source and so on, to make it weight about 6 kilograms. For the production rate, our expectation is that we can also get more than 5.5 grams per hour. But even if we have the same, the fact that reactor can be smaller and lighter, it's already a big advantage for space exploration, of course.
It's awesome.
So,
and
sorry.
Here over the numbers, it looks like a third of the weight of MOXIE at 14 grams of O2 per hour, around 6 times larger than the current design of MOXIE.
Yeah, exactly. So this, if the numbers work out correctly, in the end, we could have about 6 times better performance in terms of, let's say, kilogram of instrumentation sent to Mars. So oxygen produced per kilogram of instrumentation sent to Mars with the same power. It's the same power. For the moment, it's a long way to go, right? So there's a long way to go. But for the moment, every result that we are obtaining is confirming these numbers, or at least is not making us drift or doubt these numbers. You never know. At any moment, we can have a step back or some bad news. But for now, our progress is supporting these estimations. So we keep excited and happy. Let's see.
And then toward the end of the paper, you mentioned a full-scale system could produce 100 times more O2. So
wow. Yeah. So this the goal it's okay. This is a toy, of course. So this is a toy. It's a small machine, again, similar to MOXIE. But to give an idea, if we think now, okay, we sent someone to Mars. Let's send some astronauts to Mars, and he's there, and he needs to survive for a full day. He needs to breathe about 1 kilogram of oxygen, roughly. So if we are producing, let's say, 10 grams per hour, and let's say that we can have the solar panels fully illuminated about 4 hours, so we will produce 40 grams per hour per day, or Martian day. So that the factor of 100 comes from this. So 40 times 10 is 400. So maybe not 100, maybe 25 would be enough. But okay, something between a factor of 10 and 100 would make this already interesting, let's say at the human scale, producing enough oxygen to start thinking on supporting a real mission to Mars.
And gee whiz, I think these plasma fields, you start to wonder where else they should be and where else they could be. The opportunities there on and applications. Yeah, beyond Mars, both here on Earth, but also Venus. I think it's very promising.
Yes, okay, that's a flattering comment for me because it's my field. So of course, I believe that plasmas can be useful for life on Earth as well. I said we were working on CO2 conversion on Earth when we start thinking on Mars. So it's a somewhat similar idea. The operating conditions are different. But yeah, it's to go for production of synthetic fuels. So if you use renewable energy, we know renewable energy has this problem of intermittency and also a geographical issue. So we produce in one place on Earth and maybe we need to use it somewhere else. And we have this problem that sometimes we can have a lot of sun or wind or whatever, and we can produce a lot, maybe more than what we can consume. And in some other times, we really need energy and we don't have it available. So there is an intermediate step that is interesting, which is to store the energy. Can we store it? So if we have excess, can we store? There are no magic solutions. And if I mention storage of energy, most people will think, yeah, okay, batteries, let's put it on batteries. But we all know batteries, okay, you can store for a while, but you cannot store for a long time. And they have problems of their own. Every technology has problems of their own.
Yeah.
Our view is that we could use this excess energy to produce synthetic fuels, just with renewable energy. So if we have a surplus energy that we are not using, let's produce some gasoline or whatever. And then we can store it in a barrel and it stays there for years. And we can use it when it's necessary.
Just doing some research, and it seems like we want these plasma fields really anywhere there's gas conversion and filtration for methane, water, hydrogen, nitrogen. It sounds like a more energetic efficiencies separation.
Yeah, I use the expression, it's a molecule breaker technology. So we can convert different chemicals. Water is, of course, interesting. We can use it for decontamination. I heard about another project from colleagues in the UK that they were thinking on using it precisely for sterilization and decontamination of water for space missions. Okay, nitrogen is also interesting, mainly for fertilizer, not mainly, but to a big extent to production of fertilizers on Earth already. And also we were thinking, okay, if we start looking on our technology far away in the future, once you have the oxygen separated, the Martian atmosphere also has nitrogen. And if you mix the nitrogen with the oxygen that we have separated, then we can produce nitric oxides, which are based for fertilizer. So if we think on make agriculture on Mars, you can have also the production of fertilizers there. But going back to Earth, it's also, yeah, a molecule breaker technology for Earth that can produce or help on the production of different molecules, ammonia, different nitrogen compounds.
Yes. And you mentioned, plasma thrusters for space propulsion, and we're also reading about how proton exchange membrane fuel cells are beginning to utilize these plasma fields too, to both form water and split and reverse reaction. It's
yeah, if I understood correctly your question, we can join part of let's say electrochemical technology from plasmas with the standard electrochemical technologies, for instance, water electrolysis, and then possibilities multiply. Because one thing that is interesting of this plasma technology is that it's very versatile. I think this is the word when we are now discussing, okay, different molecules, different production of different chemicals. It's very versatile because the same machine, just by changing the gas that you feed or the way that you mix it afterwards, you can go to produce different molecules or different chemicals. So that's one.
Was really trying to model in our heads these gas flowing through this plasma field, and we're imagining this plasma charged particles spiraling in this helical geometrical shape, and whereby we can almost begin to model these and quantify the angle of collisions with the electrons and the scattering angles. And so we were wondering, like, how does the electron flow, if it's disordered or if it's ordered, and how that influences the molecular species and composition?
Yeah, this depends on the actual design that will be used. So you have for every taste, so to say. So you can design a reactor where the flow is very steady and there is no turbulence, and so you have a well-behaved system. We see the molecules flowing and the reactions taking place in a very smooth way. But you can also take advantage of mixing of different gas mixing, so to have different types of flows, to have even turbulent flow, to mix regions of hot temperature plasma with cold surrounding regions. So this is more a question of the design, the exact design. And it's possible, you are right, it's possible to take advantage of this for certain applications. So on Earth, this is a very active field of research. So in line what you were saying, so to see the different angles, to make in fact a computational fluid dynamics simulation of the full system, and see with this gas mixing how you can enhance the efficiency of the process. On Mars, it's possible to think in this type of designs, but it's maybe less critical or less a less interesting direction to explore than on Earth because of this question of weight. So we have to keep the reactor relatively simple so that it's light and that it's small. I'm not saying it's not worth to explore on Mars, but it's not as easy as on Earth because here we are not so much limited by certain restrictions. But yes, there is a zero order effect, how much we dissociate, how much atoms arrive to the membrane, and then there are all layers of complexity that add on the top of it. And of course, this flow dynamics is one of them. It's one of them.
Nice. And then with these computational models, we're wondering if how about the magnetic forces and attractions in the plasma field on the effects of dissociation?
Yeah, so the plasma that we have is weakly ionized. To put a number, it's like only 1 in 1 million of molecules is ionized, or maybe even slightly less, which means that we don't have a strong magnetic fields. So in fact, for these reactors, magnetic fields are not playing any special role. Electric fields,
But even though like the electrons, they're following the electromagnetic field lines. They're following the magnetic field lines, right?
Yeah, so you can operate a reactor that by design will have a magnetic field. So you have magnets in your reactor and try to take advantage of this configuration. But what I meant is that we don't have to worry with magnetic fields created by the electrons themselves or by the ions.
But our understanding is that based on Maxwell's equations is that the magnetic fields, they're automatically generated from the electron flow. And so there's a perpendicular magnetic vector force acting on the reactions.
It's true, but this magnetic field will be relatively weak, or it will be in fact weak enough so that we don't have to worry with it. So we don't need to take it into account in the simulations unless there is an external magnetic field. So you are right. As soon as we have electrons or ions that are moving, we have magnetic fields. But the magnitude will be very small and will not perturb the motion of the electrons. In the length scale of our reactor, it's 20 centimeters. So.
Nice. Okay, and the last thing here is we were reading about how radiation and these ionizing alpha and beta particles influence the vacancies, whereby each time the electrons hit the vacancy, there's the electrons it flips their spin and angular momentum and induces this type of skew scattering and side jumps that would be important in to monitor the membrane lifespan and all of these vacancies over time. And yes, but a lot of ground testing of
Yes, so I confess that I'm a person from the plasma side. So all these technology for the membranes is not really my specialty. So it's again our colleagues from DIFR that are developing this part. So I think I cannot really make a competent comment on such microscopic detail. So I know, or what I can say is I already said more or less. So we need to absorb the atoms. We need to charge them so that they will be transported on the vacancies. There are many design considerations here, mainly related to where, how, if you put the electrodes on the membrane, because the standard design, you need to have the supports, so this Yttria, zirconia, and then you have the electrode, and then you have the gas phase or the plasma. So you have these three components, and the transition, all this transport will be made on the interface of all this. But they are thinking on a different type of designs that precisely take advantage of the fact that you already have the plasma. Also, we pass through this very briefly. So the atoms or molecules absorb, but when you have the oxygen atoms on the membrane, they have to become negatively charged. So they can become negatively charged because we pass current on the cell. So it's a solid oxide electrolysis cell, so you can polarization, and you have electrons flowing on the electrodes, but maybe you don't need them, and you can just use the electrons from the plasma to charge negatively your adsorbed species and then transport them to the vacancies. So all this is a lot of research still in front, but this would be, if I can use the expression, would be the Graal, that we could use the electrodes only to generate the plasma, and the full system with auto adjust as to take what it needs to operate. But this is a bit far-fetched, but we still hope that maybe this is possible.
Nice. And I think it's just a few last comments here. I think it's really mind-boggling to imagine how much we could do with these hydrocarbons and the oxygen and the carbon, you know, and the water. All can synthesize a bunch of hydrocarbons in situ, beyond Earth, where we want. And I think that we could consider the plasma fields for tailpipes of cars too, and I think the fields, these plasma fields, hold great potential for Venus as well, and it's very exciting.
Yes, thank you. Yes.
Keep up the great work.
There is no magic solution, but I also believe that for this, well, to help on cars and so on, it is doable. The question is, how expensive is it? So to do.
Yeah. All right. Well, thank you so much, Vasco, for your time today and everything you're doing.
No, thank you as well for your interest in our work, and it's a pleasure to speak with you, of course.
Look forward to hopefully meeting you sometime and next time and supporting work. So
yeah, the same. Thank you.
see you. Thanks.
Bye.